Now let's go ahead and proceed and write out this system of first order differential equations to matrix form. So again, you'll notice another pattern that we're going to be using is that every time we convert a higher order differential equation to a system of first order differential equations, we then will take advantage of converting that to matrix form to allow us to simultaneously solve these first order differential equations very quickly so we can then solve the larger problem of the higher order differential equation very efficiently. Okay, so to start off, we first write the system. Okay, so first write the system so that, okay, each side is a vector. All right, so we proceed in this way. Um, just like we convert systems of equations to the augmented matrix form, this is going to remind you of that H matrix we showed at the very beginning of class. It's all coming back now in a way that's very cool. The left-hand side is going to look like a column matrix. It will say x1, x prime 1, and then it will say x prime 2 on the left-hand side. And this is going to equal our two equations, which will be 4x1, right, plus 7x2, all right, and then it's going to be minus 2x1, right, minus 5x2, like this. Then we could separate this out even further to make it really nice. We will say this is x prime 1 as before. The left-hand side won't change. X prime 2. There's our column matrix of derivatives. And the right-hand side, we can isolate the coefficients. And we have 4, 7, -2, -5. Okay. And then another column matrix of x1, x2. And if you do the matrix multiplication correctly, you'll see this becomes this easily. No issues there whatsoever. But we're not done yet. We still have to define our vector for the unknowns of x1 and x2. So we do that by saying, let us define an x vector, which I'll designate this way, to be or equal to our two unknowns, which would be x1 and x2, just like that. All right. With that being said, we can then state then what we have is x vector prime, guess we can take the derivative of a matrix, is then going to equal x prime 1, x prime 2. And that's how you take the derivative of a matrix. So you take the derivative of every element in the matrix. Okay, just so you guys know. Therefore, okay, the system can be written as x prime, that was the left-hand side, with our column of first derivatives for the unknowns, which would have been this right here. Now we're just simplifying it, and that's going to equal our coefficients, which would be 4, 7, -2, -5, and the x vector we just defined. And this actually completes the problem. Do you notice how simple this looks? How much easier this appears? How much more condensed the notation becomes? That's a lot easier to solve than this, okay? But more so, this allows us to solve very complicated systems because you know this was probably a second order differential equation, right? Probably. And then it got simplified to a set or a system of first order differential equations, okay? And so this is the process that you can use to check yourself against. For example, on your final, I'll ask you to do a few of these conversions, one or two, and then I'll ask you to solve that system for those unknowns, for that x vector in particular, which will solve a larger system above it, okay? And then you can imagine for even larger systems or even larger matrices or systems of differential equations, solving that system allows you to solve an even bigger system above it, an even higher order of differential equations. Okay, so that's what I wanted to show you for this example. And then um, in the next video, I'll show you how to convert one of the previous examples we just did to matrix form, and then proceed to solve one of these as we go. See you soon.